And what we could do is when we made a equivalent one, so that we wanted little bit better performances, we made a indigenous antenna, and then now the performance is much better. In fact, the original OEM, since they were taking this antenna from another company, they have now looked at us for exporting this antenna. So these are another topic. And IFF, as I said, yes, we have got these systems. We have IFF in three variants, where we have only interrogator configuration, or a transponder, or a combined interrogator transponder configuration. And the different ICAO standards have been followed, and these systems have already been developed using the digital monopole statement. So another aspect, as we talked about beyond line of sight coverage, we have a SATCOM antenna on top. So initially we had the airborne antenna was of dish-based, and so the volume that it takes on the on board the aircraft can lead to higher drag count, reducing the endurance. So we are also now looking at phase delay configuration, but with the vast country, the area that it involves and the position of the satellite, we need coverage of almost 5 degrees to about 85 degrees coverage. That test on board the aircraft on ground, we do a RF compatibility test, and then radiated and conducted emission tests. And coming to the integration of all these on the aircraft, first is we did the lab level integration of the subsystems in standalone mode, then with simulators representing other subsystems, rooftop testing, so that what we did is all the antennas are kept on a rooftop, considering the cable loss and compensating for that as far as performance is concerned, and checking whether all of them in an integrated fashion work, and full integration with actual units. And this was also done with user participation. So this rig was used as a platform for actually clearance from the user before it is before the mission systems are integrated on the aircraft. And we also had a flying test bed for some of the systems. Our users were very demanding. So as we can see, so many systems they had asked on such a small aircraft, but that challenge we took it up because of system engineering approach. We could see that all of them are integrated and is fully operational, and very happy to say that even in as per the media.
Sir is an accomplished researcher in the field of advanced antenna and microwave systems. Sir completed his PhD from the Center of Applied Research in Electronics at IIT Delhi in 2018. He is currently serving as an assistant professor at IIT Patna and has previously held positions at IIT Jammu and as a postdoctoral researcher at KAIST, South Korea. He is a recipient of prestigious international awards, including the Young Scientist Award 2021 by URSI USA and fellowships from Brain Korea 21 and GCORE case for research excellence. Sir has authored over 60 publications, including journal and is regular reviewer for top-tier journals such as IEEE, APS, and MDT transactions. His research focuses on millimeter wave antenna design for 5G and beyond, meta surfaces, microsatellite reflect array antennas, and SDR-based radar systems. So please join me with a warm welcome, Dr. Amit Kumar Singh.
I thank Dr. Ramakrishna, Dr. Bharti ma'am, and Osmania University students and chapter of IEEE APS for inviting the complete delegation. And the main force behind this particular workshop, Dr. Rao, and the complete BAMS team, BAMS 2025, who supported in having this particular workshop. And as part of this today, I'm going to talk on these two very interesting topics. And how to plan one is the intelligent surfaces, and the second one is antennas, particularly for millimeter wave and sub-terahertz, 6G applications in general. So, as you see, the major title, intelligent surface and antennas. So, in general, you can have understanding. Intelligent surface means a surface with some intelligence. Those intelligence can be inbuilt because of having several uses. Depending on the requirement, those intelligence can be inbuilt on the surface by having so many sub-electronic systems. And depending on that, these surfaces may act for so many various operations. So when we talk about surfaces, these surfaces can be of several types. One completely reflective, one completely transmissive, and another one can be simultaneous transmit and reflect both. So these are the three scenarios on which this kind of intelligent surfaces can act for. So complete transmissive, complete reflective, and simultaneous transmit and reflect. And as far as antennas are concerned, there can be several types of antennas. However, before going to these two topics, my major emphasis will be why and how to have these two, particularly for millimeter wave and sub-terahertz. There are some challenges, that's why these two solutions are. And in particular, when we will discuss these two things, I will try to discuss these coding, so and so forth. However, here the multiplexing is with respect to phase at the same given time, same given frequency, and all. So its benefit is in 6G, where the promises are of data rate of throughput of 100 Gbps. Getting 100 Gbps kind of data rate throughput of electronic backgrounds, RF backing as well as RF fronting. So, to minimize the technology requirements, the cost, the power requirements and all, this is one of the most promising techniques. The second one is this RIS. The requirement for this RIS is particularly for when you have in our earlier lectures, you have seen in the morning session that when frequencies are moving towards higher side, they cannot propagate for longer distances because of their own constraints. So, when we have the millimeter waves and sub-terahertz, what are its uses? You install a kind of active repeaters, general repeaters which we used to have as of now for our 5G, 4G kind of uses. However, if you are going to design those kind of repeaters for 6G aspects, and if you are going to install those many repeaters, particularly for millimeter or sub-terahertz, those kind of bands, the cost is going to be so much. At the same time, the power requirement, the deployment, technology, and all, so much of challenge associated. That's why this RIS is a kind of this reflecting intelligent surfaces, reconfigurable intelligent surfaces. They are going to act like a kind of passive repeaters. The benefits, what this RIS is going to give us is, this RIS is going to provide optimized beamforming. When we say optimized beamforming, irrespective of the nature of this RIS, either reflecting or transmission and reflection both at a time, this RIS can provide optimized beamforming. Now, in our discussion, I will show you some of the near field usage of this RIS, some of the far field usage of this RIS, where we have designed some of the near field RIS, transmission as well as reflection type, and try to watch the beamforming in some of the desired directions. I will also try to show how this RIS can be used. It's a very excellent opportunity to use our technology, to use our potential to design and develop the technology, where government is supporting all of our efforts, including industry people also supporting our stuffs. So, in that sequence, Government of India have proposed, and that particular project is in progress, two test beds related to 6G. One is this Bharat 6G terahertz test bed. The second one is advanced optical 6G test bed. So the Bharat 6G terahertz, four are the major team members, the consortium members. Samir, one of the well-known society for electromagnetics and RF microwave related applications, which comes in the Ministry of Electronics and IT, IIT Chennai, IIT Patna, IIT Kolkata. This complete initiative is supported by Ministry of Communication, Department of Telecom, and CMAS. So, under this initiative itself, particularly related to intelligent reflecting surfaces. So, one of the figure demonstrates as far as possible indoor scenario. How intelligent reflecting surfaces can be deployed and what are the possible in general use cases can be. At the same time, in second figure, RIS deployments and use cases as far as possible for outdoor environments. So wherever you see the possibility to enhance the signal characteristic, irrespective of frequency band, this RIS can be
other things. Yeah, this is the transmitter block and that is the antenna. Basically, if we see like this, whatever part we removed before, that is the signal domain, and this is the EM simulation domain, and in the end again it is signal flow domain. The ones which are highlighted in blue are the ideal blocks, the vehicles, and microstrips. You can add like loss, dielectric loss, tandy, everything, the conductor loss. And once we are happy with the ideal design, we could replace the vehicle with designs from RFPCB, and also we could replace the phase shifters with designs from RFPCB. So these are the EM simulations. Initially, so this is how generally a system is designed. Initially, we see the block diagram in textbook or somewhere. We design an ideal block diagram in software. Then if once we are happy with the specification, system specification, we'll try to replace one block with the EM simulation blocks. And finally, we could replace even the EM simulation blocks with the tested S parameter data to see it all works as we expected. That is the antenna array which we simulated in antenna toolbox. So antenna toolbox is used for the antenna array. RFPCB toolbox is used for the passive elements, whatever is. This is a glimpse of antenna array designer app. We have like some choices of the lattice structure of the array, rectangular, circular, linear, etc. And so first we need to select the lattice. We need to select the element which goes into this lattice, and then we need to select the backing. What kind of reflector we need. If we don't need any reflector, we can put no backing. Here, a patch is selected, and once the design frequency is inputted here, it will design the spacings and everything for you. The antenna design will be ready, and we can, once it is designed, you can export it as an object. If you are interested in command line workflow, we can also use command line workflow where the first line, this is like frequency is defined, then the dipole blade is designed at that frequency. The basic dipole is asked, and the dipole blade is designed at that frequency.
I now request Dr. Christopher Pimau sir, Dr. Chavi and Desmond Sim sir, Dr. G. Ramakrishna sir, and Dr. A. Bharti ma'am to present token of gratitude to our esteemed speaker. As we have come to your active participation, I request you all to join us. Thank you.